So good afternoon, everyone. This is a joint work in between collaborations of University of Illinois and IBM T.J. Watson Research Center and the University of Central Florida. So we got a couple of collaborators, and I'm the second author over there. At the beginning of this talk, I'd like to introduce this idea of network embedding and some problem that can be defined on this in this context. So first, I think everybody is familiar with vector embedding for certain kinds of objects. That's basically the first idea of doing data analysis. Basically, everything in the real world need to be represented as a vector to be started with any machine learning or data mining algorithm. So we also call this kind of vector representation as features or representations. And the goal is usually we not use just the raw format of the data, like pixels of the images or just the raw text, but instead we have some lower dimension representation that can retain the useful information. By say useful, we mean it can be used to do some tasks we're interested in, and also throwing away those irrelevant data. So in the literature nowadays, people use a lot of learning methods to do this, to find such embedding for objects. Sometimes this learning is guided by labels. And for example, if we have a class labels on images, then we can do classification, and we can get the intermediate representations as good features. Or sometimes we just look at the data distribution itself, and we can by doing this, we are doing unsupervised embedding learning. For example, the simplest method like principal component analysis, we just make a Gaussian assumption and try to get the most significant dimensions of the data. Now, we noticed that there are certain kind of data that are quite available these days that are data with the network structure. For example, we have the web data, we have some data from the social network like Facebook and Twitters. And the one common properties of these data set are they not only have individual nodes, but they have very massive available links in between those nodes. And these links are supposed to have some valuable information. In other words, if two nodes are linked together, then there must be a reason for them to link together. So we assume there are rich information left in these links, but nowadays there's not too much method that can use this link information to help the learning of the embedding on the nodes. So the goal of this work is whether we can do embedding learning on the nodes of the network with the help of the link structures. And so how do we do that? The short answer is we keep some. We try to learn this. We try to learn this embedding while keeping some properties of the network. So now let's go to some more detailed definition. So we define this heterogeneous network as a network with multiple types of objects. For example, in this paper, we're interested in two types of objects. One is image, the other one is text or natural languages. And there could be links, multiple types of links also. Some links lies in between same type of object, like image to image, and some links lies across those different types. We also call this we also interchangeably will call types as modalities. So these are intramodality links and intermodality links. And we model this network as an undirected graph, which means we don't care about direction, even if these are natural in the original data. And we assume there are some content information on each node. The assumption is true for image and text. on image, the content information is just the raw pixels in a 4D tensor format. And on text, these can be the raw text or some simply processed feature of these tasks. So in this work, we limited ourselves to image and text, and with 3 types of links between them. So now we can have the big picture of this these settings of this problem and various definition. We have a heterogeneous network with images and text, and some links within and across the 2 modalities, and we want to find an embedding space to hold both of the 2 modalities. So there are 2 challenges. The first one is how can we make use of the links to guide this embedding learning, and the second one is, since there are two or multiple type of modalities, how can we use links to project them into the same place? So once we learn this kind of common embedding space, this could be very useful for any other tasks. So this is just the benefit of feature learning. One of the major challenges of this learning problem is usually we have, because of the structure of the graph, usually we have much more links comparing with the number of nodes. So we need to constrain our learning algorithm to be the simplest one, to be computationally feasible. And also the other challenge we already mentioned is how do we deal with multimodality data. So to answer the question, now we go to the first step of method. So this is the formulation we used to embed different type of object. Basically, we have 2 individual projection matrix. Start from assuming that we already have some kind of vector representation for both for 2 type of objects. Then we define the two matrix U and V as their own embeddings, and we try to learn the 2 together. We constrain the embedding as linear because of the requirement for simple algorithms, and also here by doing this, we require the target dimension to be a grid, and that allows us to define a common cost functions within the target space. So the assumption we relied on to do this feature learning is we assume, basically we assume if two objects are linked together, they should stay close to each other in the embedding space. This is usually true in real-world data set, like if 2 images are from linked, if 2 websites are linked together, they are tend to be more similar to comparing with those unlinked websites. The same as like two people on the social network might have some common interest if they are linked together. So once we have this assumption, the way we enforce this closer relationship between linked nodes are by using this distance measure. So here we use the inner product between 2 objects as their distance, and we can set up a decision function based on the distance that is used to predict the link. So in short words, the object function is we can use we try to predict whether there's a link between 2 objects just based on their distance within this embedding space. And by learning this objective function jointly on either within the same modality or between modality, we can enforce this final embedding to be consistent with the original network where we are learning from. So let's go back to the big picture. Now we have in answer to the 2 questions. The first one, how do we use the links, the network structure? The answer is we we make our model predicting the link and preserving. In that case, we can preserve the network information. And the second one is how do we deal with cross-modality data. So here we assume there exist some links across those modality, and these links can serve as a constraint to do the joint optimization. Thank you. So the second part is, besides just do a linear projection between the two modalities, we also use some deep models in this framework. So previously we assumed there's already a representation of the two individual type of objects. However, we cannot just use this raw data such as pixels or content. But here we choose to use deep learning combined with this this embedding learning because of three benefits provided by deep learning method. The first one is across deep learning provide model capacity. These are the state of the art of many things like images and text. But more importantly, deep learning is flexible because the learning is just gradient based. We can easily plug in the modules of our embedding learning upon an existing deep network, such as convolutional neural network, and we pass the gradient down to this feature learning, the feature part of the deep the network, and this can be an end-to-end to learning, and that usually provide better results. And the third part is just the deep learning require a smaller amount of memory to do the optimization, and that is very useful in this learning from network setting. So in our setting, we use AlexNet, which was a state of the art 2 years ago, as the image module, and it is pre-trained on ImageNet 1000 class classification problem. And on the text, we use just we just use one fully connected layer. So then this is a detailed model structure. You can see we sample 3 type of pairs from the network: the image to image, image to text, and text to image, and text to text. And we have 3 networks, but they shared certain components. And then we have 3 loss functions upon them to predict 3 different type of edges. So now we go to the experiment setting. When evaluating this our work, we try to answer 3 questions. The first one is, since the training objective is to predicting the edge, in other words, reconstruct the network. So how well can the network be reconstructed just using the embedding space? The second question is, if we just train this embedding on a single modality, how well is this learned feature? And the third one is, what's the performance if we do a 2 modality? And we use one single modality data set, the block catalog, and the NUS-wide as a cross-modality data set. For the first question, we test our performance on the block catalog structure, on the block catalog data set. So in this data set, the edges are actual social following relationship between different blocks. So and the content features are just the raw text. We extract the TF-IDF features from the block text and learn this embedding, and then we just do a thresholding on the inner product scores to predict the edges. So using a 2 layers neural network, we can get roughly 83% accuracy on edge prediction. Since this is a new task, we don't have baseline for this number. Now, a more important question is, since this is embedding learning or feature learning, what is the performance of the embedding space in other tasks? So to eliminate the influence of different methods, we just use nearest neighbor classification. in this block catalog data set, there are 6 class labels on each data point. So we do this 6 class classification and compare between different features. So you can see from the plot, the red bar, from right to the left, the second one is the red bar, is actually the performance of our model. And the best one is our model followed by a supervised fine-tune using a softmax. So even without any fine-tune, this feature is already better than other methods. And with fine-tune, it can there is still a large room for improvement. Okay, now we go to this cross-modality setting. On NUS dataset, there are images, and it's a very rich data set. There are images, there are text, and there are additional multi-labels on those things. So, yeah, thank you. So here we just use the correspondence between image and text as the cross-modality links. And there's no ground truth links for this data set. So we assume 2 images or 2 texts are linked together if they share one common attribute. And using that, we can get a very dense network. Then we randomly sample the edges in that network at the degree of 30 edges per node. So we evaluate this performance using first, we're using the, again, this is a multi-label classification. We use the mean average precision comparing with our method without the content learning, which means we just learn the final linear projection layer and other another traditional method. So you can see the improvement just by enable the joint learning. If you compare the last column with the linear version of last column. And also, it's natural the natural task to evaluate the cross-modality embedding is to do retrieval. So here we use the standard benchmark on that data set to do the retrieval in this joint space. And this method is much better than just than those methods which doesn't take into the network structure into account. So we conclude in this work that we are able to, there are 2 points in this work. The first one is we are actually able to get some useful information from network as long as the network, the links in network have some sense, some correlation on the actual content features. And here we make the assumption that linked nodes need to stay together, stay closer in the embedding space. And the second conclusion is, by doing this, if we have different type of links, then we can actually bridge between different embedding space of different type of objects, and which is very useful to do cross-modality tasks. So in the future work, I think we might exploit not only just the 2 nodes links in the network, but also employ whether we can make use of cliques or like triangles, a more complex structure in network. And also here we use traditional features on text, but nowadays there are also deep learning methods on text which can be directly connected to this framework. In that case, the performance might be further improved. Okay, that's the end of the talk. Thank you.
So that is time for some questions now. Well, at least I have one, because what I missed was something about the runtime.
Mm-hmm.
How much is in the embedding and then in the further steps? That is of interest.
What do you mean by runtime? The testing time, computational cost, or you mean the computation, or?
Yeah.
So since this is just a feed-forward neural network, then most of the time spent are at the training stage. And testing is basically like a number of matrix production.
Yeah, that's why I wanted to know how long is the training. I mean, these embeddings normally take quite some time in computation.
Yeah, yes. So it depends on the data set. So on the larger data set, we use about 3 days training on for one training session on 2 GPU machine because we need GPU to process the images. And on the smaller, the block catalog is just a couple hours to finish the training.
Okay.
Mm-hmm.
Are there other questions? Yeah.
I have a question for the image to text. For the image to text feature similarity, what did you use? And does it make sense to run it across all the network? Yeah.
You mean how do we build the links, right?
Yes.
So yeah, that's a very good question. So to here, because the nature of that data set is image and text are linked together. So there's a one-to-one correspondence.
Yes.
We just use that as the links.
Okay, so you didn't use it for all the network.
Yes.
Thanks.
Okay, so let's thank the speaker again.